Bundles are incredibly common in my experience in applied category theory, just as are sliced categories, what we just discussed. And bundles provide this very helpful lens, this sort of simple point of reference for understanding sheaves and pre-sheaves. And there's all these constructions and ideas in category theory, many of which are going to be very important for our traversal of sheaves, like sections and fibers that are tied in. But there's some really broader ideas that are very powerful, like the idea of classifying maps and classifying spaces. The category of elements is something we've seen. These are tied in with bundles. Notationally and conceptually, it's really useful to be familiar with bundles. So, at an intuitive level, what's a bundle? Well, look, a bundle, my crude view of it, and it probably merits a lot of refinement, is bundles allow association of values from different categories and spaces with some base space. And I'd say different here in the sense that it's typed. Different, they can be of different types. And bundles range in sophistication depending on the nature of the space. So we have bundles over sets, we have bundles over topological spaces, and we have bundles over categories. And sheaves can be viewed as bundles with some added topological structure. And every sheaf gives rise to a bundle. Bundles are closely related to sheaves. And the notation and the terminology here is similar. So the basic arrangement here with a bundle is we have some base space. We're going to call it I. And this is rather asymmetric. We have a base space, and then we have arranged over the base space, arranged over each point in the base space, as it were. We have a fiber here containing some other space. This upper space, Daniel Rosiak in the book calls it stock space. I've also heard it called the total space. Sometimes the base space is denoted B and the upper space is denoted E. But you'll notice that a critical component, as always with category theory, you should be thinking about not just what are the things, but what are the morphisms? And there's a key morphism here, P, that projects down from the total space, these fibers, the stock space, in the stock space, down to the base space. So all of these are diagrammatically arranged suggestively over their corresponding point in the base space. Okay. Now, when these are sets, the points are elements of this set down here. And that's very common and very, very practical. Even there, you'll notice that like the size of the stalks may be different because the number of elements that map into this is different. But it's very common if these are sets and these are sets. They can be topological spaces in which each of these would also be a element, but there'd be a topological set of, there'd be a topology which induces maps down here and induces maps up here. And these can be categories, in which case these are objects and you have category up at the top. But in any of these, P is some sort of structure preserving mapping where structure really doesn't really exist for sets to be preserved. Okay, so we have a stock space or total space, fibers are in it, and the base space. And each fiber characterizes the things that map down to the corresponding point in base space that's put under it. So you notice this fiber is specific to I, hence it's labeled Y sub I. This is a wonderful diagram from Daniel Wozniak's Chief Theory through Examples. J here is the point in the base space, and it has this stalk over at Y sub J. This fiber here has 3 points in it. If this is a set, this might be a set of 5 elements that all map to I through P. All these, if we're dealing with sets, all these map down to J. All these 4 map down to K. Now, what differs again between these is that with things like topological space or categories, there are some morphisms that relate these to each other that constrain what's possible in terms of what's going on up here and down here. They're not solitudes. They're not just you pick one from here, one from here, one from here, one from here, willy-nilly. You've got more constraints, just like up on the board with those mappings from topological spaces. You can't map willy-nilly. Okay, so for the discrete case, the case with sets, we have a base space for set I. The stalk is the disjoint union, sometimes called a tagged union, like this. In other words, each of these stalks knows there's no confusion that this point here, which one it's associated with. It knows it's associated with I. It knows it's associated with J. And so any element or so-called germ here of Y sub I maps down to I. That's why it's over I. Are we comfortable with that? There's nothing like deep here about it. It's just like these are all the things that map down to I. These are all the things that map down to J. And it's very useful to think of it this way. So P maps from the total space down to the base space. And Y sub I, and this is important, is just the inverse image or pre-image of I for P, right? It's all the things that map to I. Are we comfortable with this? So these are all the things that map to I. Okay. Now, I'd like to orient you to a little bit of intuition that I use and some others I've seen using with respect to this. I like to think of this, again, it's kind of asymmetric. I find it helpful sometimes to think of these as like parameters, like this is parameter I, and these are the choices of values of the parameter I. It can be in this age group or this age group or this age group or this age group or what have you. Maybe this is a choice of province, a set of choices for the province or something like that. But it's a little bit more subtle than that. Because often this is a set that itself we can draw elements from. But I'd like to think of sort of these as choices of possible values for this.
What I'm thinking, right, with this, I think each object in the base space is like a knowledge graph.
Right.
Knowledge graph.
Right.
And the P, the reverse image of P is like you find a representation of
That's right.
Of a knowledge, like a knowledge graph.
That's right. a particular set of possibilities or something. Yeah, so this could be like another way to think of it is like this might be the set of values of what interventions are in place in Prince Albert. This is what interventions are in place for Saskatoon. This is what interventions are in place for Regina. And they have different sets of possible interventions, perhaps, that they're considering. But at any one time, you might have one in place there, one in place here, one type of public health order for this, one type of public health order for this, one type of public health order for this. Now, it's worth noting that we just talked about bundles, and the very notation here, John Bies tells me, the notation for slice over, like, C/X is because like X is down here. And the elements of C up here map down to X. And they map down to a comparable X. And if you have morphisms between these sort of bundles, the maps over the fibers that map over I, for example, there'll be a mapping from this fiber, y sub I, to the y prime sub I, but not y prime sub j, y prime sub I. So if you're mapping between bundles, so I understand it, this fiber over I from from the first bundle will go to the comparable fiber over I for the other bundle. So there's this kind of notation that they're over this common thing I. Okay. So we have again here morphisms or commuting triangles that honor the mappings to I. So we're mapping fibers to corresponding fibers as we have these categories. So these are bundles, and the objects are a set A and a function. So this is this and a function from A to I, and morphisms. Maybe a morphism, maybe not a function. I think it's a morphism more generally. And then morphisms here in this category bund are involving mappings from A to B that honor the mappings to I. So this should remind you very much of the slice idea, where we're sort of we're honoring and preserving this mapping to structure when we map between the fibers. Okay, so P is a function. And what function is depicted if we thought about P as a function that's mapping down to this base space, what function is it? So what's its domain? And what's its codomain? In the top. So A, B, C, D, E, F, right? What's its codomain? 1, 2, 3. Okay. What does A map to? 1. What does B map to? 2, C. 1, D. 3, E, and F, both to 2, right? Okay, are we comfortable with that? This is P is a mapping down. Here we're just depicting sets, right? This is a set. Okay. Now, we're going to now define a notion of a section, and this is absolutely central to sheaves. Sheaves are all about finding legal sections, sections that honor certain constraints. I'd like to talk about how these apply to bundles because it's a great intuition building exercise how they apply for sheaves. Okay, a section for a bundle that has a P is a map in the opposite direction, S. It maps from each of these to one of these for each. It kind of picks one for each, but it does that in a way that has a sensible property. I mean, the way that that's stated is, look, it's a map from this to this, such that if we perform that map and then we map back down, we get identity. Meaning, if we're at like 1 and we pick one of these, say A, and then we map down with P, well, we get 1, right? 2, if we pick E, and then we map down with P, we get 2. 3, map up, D, only one choice, right? Map down, we get 3. Now, in other words, it's an assignment of one of these objects in the total space, in the fiber. So for a given element here, if we're doing sense down here, it selects an element in the fiber corresponding to that element. You get that sense? Are we okay with that? 2, it picks one of these. 3, it picks one of these. This is a very useful notion. You notice it's, in a sense, value-dependent types, or how to put it, like the type of this will depend which one you're looking at. Like this has 3 choices. This only has 1. So there's a notion in programming language of dependent types. So you might have a type which depends on a value, like an integer of size b, where b is some value. And here you get a little bit of a flavor of it, depending where you are here. You're at 2 or 1 or 3. If you think about these as different points in a space, like a topological space, the set of choices may differ here. This turns out to be really, really useful compared to just saying, well, it's mapping from this to A, B, C, D, E, F. You actually capture more structure here. You're capturing more structure. 1 can only map to these 2. 2 can only map to these 3. Okay. Now, the nature of map P down and the nature of map up S up, the section, we call this the section if it honors those properties or achieves those properties. Those maps, the nature of them will differ between types of spaces, right? So for sets, they're functions. They're simple functions. And that's going to take us quite far in terms of intuition, where this is a set and this is these fibers or sets. Fibers over these stalks up, right? Yeah. For topological spaces, this will be a topological space. This will be a topological space. Therefore, they're more structured. These are not independent anymore. Like they've got to cohere, right? Like what's going on here might affect what's going on over here to a certain degree. But these are continuous functions. What's going on there is also not independent. And then with categories, these are functors. This would be functors down. Okay, so I think sounds like from your reactions, you look pretty comfortable. Sanity check. I've shown 2 sections here. Section 1 is on the left, section 2 is on the right. What values are assigned to, what value is assigned to 1 for section 1? A. For for 2, E for 3, D. Good. Okay. On the right, what section, this is a different section, to be clear. What value is assigned to 1? C for 2, B, and 3, D, the only choice. So these are 2 different sections here. Now, this may seem sort of unconstrained here, and it was set. There's really little constraints on this. I mean, each set is a category where each set has very little structure to it, right? It has no structure. So and we have discrete choices here. We could choose 1 here, 1 here, and 1 here. Thank you very much. Just make separate choices. When we get to topological spaces and functors, we're going to have much richer set of interdependencies that are going to limit what we can choose accordingly. So that, we need P and P inverse, or S, the section, to be continuous maps. Just like up there, it wasn't a matter of just any old map between the sets. It has to preserve locality. It has to map things that are together in one to things that are consistently together in the other, amongst other things. Remember this condition with open sets. If you map to an open set, its pre-image has to be an open set, etc. Okay. Let's talk though about. Okay, so we have cross sections of this thing. Now, I think you'd agree that given this sort of situation, P, this defines what P is, right? To be clear, this is specifying P. Does this specify a section? Does this picture specify a section? No. This type of picture specifies a section for a set. This does not, but this does specify P, right? A and C mapped down to 1. E, B, F mapped down to 2. C maps to 3, right? We're comfortable with that idea? Okay. So we could define for a given total space, Y, it's the thing on the top, space on the top, a bottom space, a base space X, and P mapping down from Y to X. We can define a set of cross sections for any U that's a subset of X, right? So you might be like 1 and 2. Or it might be 2 and 3. Or it might be 1 and 3. For any of them, we can define the set of all cross sections over U for this bundle as set of S's. So these functions going upwards, going from U to Y, that's to the upper space from the subset of the base space, like 1 and 2. We have an S mapping up such that this little property that you do S and then you do P, you get ID on X, right? That's maintained. So in other words, it's picking, like if U is 1 and 2, what would that do? It would pick what? This is the set of all possible what? Set of all what? Well, how many things are in this cross section? If you were 1 and 2, how many choices would there be of sections here? If these are sets like this, how many choice of sections would there be? I'll do it on this. How many choice of sections would there be that are consistent?
6.
6. Yeah, we have 2 here, 3 here. There's no constraints imposed by topology or continuity, rather, or the rules of the category, what have you. So be 6, right? If we considered all 3, how many would it be? 6. Still 6. if you were just one, how many sections would there be? Two. Yeah. Right? Okay. So this notation will be of great importance in the sheaf context when we're coming into. We'll see this all the time. Set of all cross sections. For sheaves, this will be like our topological space, and this will be what the behaviors being exhibited at this point in the topological space. This point in the topological space. This point in the topological space. Are we okay with that idea? Okay. And sections will be the name of the game. We're interested in a consistent picture for sheaves about what's going on across all of our space, the whole of Saskatchewan, northern Saskatchewan, northeast, northwest, mid-east, midwest, southeast, southwest, south, etc. Different cities, they all have to give a consistent picture of what's going on. And there won't be solitudes. It'll be like they'll have to cohere in some sensible way. But look at this. There's more structure here. Yeah. Let's think about this. Before we get there, before all these linkages between policy, let's think about some basics, right? So we were just talking if U is a subset of X, we could consider the subset, we could consider it for subset U, the set of all sections. So let's consider, like, remember we considered 1 and 2 in the set of all sections, all 6 of them. That's what Nasran correctly said. But look, if there's a V within U, say 1 inside of 1, 2, like that's a subset of 1, 2, right? If we have that, then if we know it over 1, 2, we know it over 1, right? So we can always map from the bigger area, 1, 2 here, down to it over 1, right? We just restrict the section to its domain, right? So we just take this and we restrict it to a smaller subset, right? And that indeed works. Given a section over this, we can always narrow it down to be a section over any subarea, right? Does that make sense? That just comes from the inclusion structure and standard with a pre-sheaf. It's standard pre-sheaf stuff. Are people comfortable with that? This is again, it's getting very important for a discussion of sheaves. But really, this is a pre-sheaf property, being able to narrow down. Okay. Now, right. Maybe we'll talk a little bit about, yeah, let me go forward to talk about gluing here for sets, because I think it's a key notion. This is a diagram. I took my diagrams quite heavily in this time for, sheaf theory 3 examples, and by 7 sketches, also has some good diagrams. And this one is from 7 sketches. Excuse me. So the idea of gluing here will be, if we have a section from, let's say, J and K. So J and K are in the base space. Each of them has a fiber over it. And the section involves a choice of a particular element of the fiber over J and a particular element of the fiber over K, right? So if we have that for the subset of the base space JK, it's a set. It's a subset of all of it for the base space. We're thinking of this for set-based examples. And we have it for KL as well. It's a subset. Then there's an obvious constraint here we wish to impose. We wish to impose in particular that if we have this component and we narrow it down to K, so if we have KL, section over that, and we narrow it down to K, that should be the same as what? Fill in the thought. Finish the thought. Having it for JK and narrowing it to K. If we have that, we have what's called a matching family, and we can glue them together, right? Because they match over K. This has J, it has K, and K's value is the same. And this has L here. So this should remind you a lot of push-outs. Like we glue around the common things, right? Like we glue two causal loop diagrams together around common vertices, or we glue two graphs along an edge and the vertices of that edge, right? To remind you of sticking the Tinker toys together, right? If we just had these side by side, it'd be like the Tinker toys next to each other. But here we have a common point. We have like the little round thing. And so you stick these into that. It's just one round thing sticking together J and L with this common point. And we can glue them together into a global section here on JKL. Global because it obtains for all of it. And sheaf conditions are going to stipulate this gluing property, that we're going to have gluing, that if we narrow it down, these two must match. And a lot of what we'll be doing with sheaves is ensuring that. Okay, so that's a little bit where we're going with that. I want to talk, though, about bundles. We've been talking about it for sets. I want to talk about them for topological spaces. For topological spaces, we have more structure. We have more constraints. It's not just any old map from this set to this set, any more up on the board than up on the board there. We had any old map, from the set ABCD to the set 1, 2, 3, right? That we had that up on the board. Remember that? And we saw that only certain types of maps are going to be continuous maps, are going to abide by the intuitive constraint that things that appear together in topology Y at the top appear together in topology X at the bottom. If one appears, the other appears. Or the more rigorous abstract definition that the pre-image of anything mapped into an open set, any open set in the base, the pre-image of that has to be an open set in the top. So that's going to constrain our functions, right? There'll be some functions that, from a set theoretic perspective, look just fine. I mean, what's the matter with that? But aren't going to be continuous when it comes to the topologies, this extra structure, right? Okay, so let's talk about these things with topological spaces. Because when we're dealing with sheaves, we're going to be dealing centrally with topologies. We're going to be dealing because we care about data living over a topology. We're going to have this space down here being topologies. We're going to have data over it that needs to be consistent with what it depicts as going over different points in the topology over this so-called site down here. Okay. So let's talk about the bundle involving topological spaces. Okay, so the overall picture here, right, is very similar. This is a topological space. This is a topological space will be the idea. And map P down is not just any old set-based map, although, the topological spaces each involve a set. They also involve these opens, right? And this has to be this set of open sets associated with their and associated with them. And there's a continuous map here down from the top to the bottom that has to be in place, P. Now, as Rosiak notes, a bundle involving topological spaces is also an object in slice category. The slice category top over X, so the category of topological spaces. The objects are of top are topological spaces, Y and tau, but the objects in top slice over X are a Y and tau topology together with a topological map, a continuous map, I should say, from this topology to the topology X. And morphisms are continuous maps making the bundle triangle commute. So, that honor this mapping down to it, right? And Rosia comments, we think of a bundle here as the index family of fibers, indexed because like there's one for each thing, a point in the base, X, glued together by, so now we have fibers glued together by the topology of X. They have to cohere. They have to kind of play together nicely. What's depicted here is not a solitude for what's depicted here. It has to be consistent, right? It has to be consistent with what's going on here. Okay. Now, this is getting to a point. Some of this I didn't fully grok, but I understood enough of it to be in the right area. But I'm going to be explaining book learning here. So, given a bundle here for topological spaces, let's consider an open. So remember, these are topological spaces. They have sets of opens, right? We're going to consider an open subset of X, the base. And we're going to consider a restriction going up from that, just like we did before. Remember with 2 and 1 and 2? Okay, so, this should not say P of U to U. It should say P of U, P to minus to Y, forming a bundle over U. Okay. Now, we have a situation here where we have an entire space, Y, and we have a base space. So this is the total space, the full total space. And this is the base space X. And this is a monomorphism. This is like inclusion of U in X. U is a open subset of X. So this is a monomorphism. This too is a monomorphism. This is a pullback square, in case you don't recognize it. A pullback square. This is a monomorphism. This is a monomorphism. And we can pull this back to operate on this. This is like the inverse image for U. So this is like the subset of Y that applies over U, and that projects down from U or maps down from U via P over U, restricted to U. It's P restricted to U. And what Daniel Rosiak says, and I need to grok why this must be, because it's a pullback square, this must commute, right? If you go this way, it has to be the same as that and that. So if you map down to certain X here, you have to map down to the same X here. Okay. Now, what he says is, look, this triangle commute. So if you, S is basically going up from U. Remember, S is the upwards map. It's going S. It's going up from U to Y. That's the upper component, the section. And then it's coming down with P. Has to be the same as what you get if you take this inclusion into X. In other words, if you go up with the section to a fiber in Y, say, and then you come down with P to a particular point in the base space. So if you go up with a section and then you come down, you should be in the same place as it was with U. So he says this is S and then P equals I, but he also comments that's equal to ID on U. In other words, this is just, you stay in the same place in U. So if you go up and come down, you're going to stay in the same place I. I'd say if this commutes, this also needs to commute like this, which, and I'd want to think about if you come down within U and then you go up via S, this, it has to be that this maps down to, that this inclusion maps to that point in Y. Again, I need to better understand that.
The reverse image of view, view is from, no. That's right. Yeah, wait.
Sorry, this one?
Yeah, this one. Your sentence, the first sentence, then the description to you actually is reverse image of view to you rather than what.
Oh, to you?
Yeah, exactly.
Really? To you?
Yeah.
Okay.
Yeah, if you look at the book, 256.
Okay.
The P clearly restricts, on page 256.
Yeah.
8.1.2. Did you see the commuting square?
Yeah.
The paragraph above that, the PU is that actually reverse mapping of U to U.
Oh.
That would be in line with the diagram.
Oh, that makes sense. Of course. Yes, right. Because it's P inverse down. It says P sub U, so it's P inverse down. Yes, of course. Right. Thank you. Yeah, that's exactly right. So that's this one here.
Yeah, you have a restriction map.
It's a restriction map.
Yeah, and it's outside.
That's right. So this is kind of P pulled back to operate on the subset.
Yeah.
And then you have still a section from this has to abide by this property that if you take this section and then you come down with P, it has to be the same as just staying in place with where you were at with U. Yeah. So he actually says at the very last two lines there, the composite P after S, so that's this one, P after S, is equal to the inclusion I, that is P after S equals ID on U. Yeah.
But P sub U is P restricted to just the main U.
So, yes, I think what this is like, if this is U, you have P restricted to codomain U. Like this is P inverse of U.
Yeah.
And it's to be clear, I think P inverse of U is the coproduct of this and this. Remember, it's this tagged union thing. The fiber is like tagged union, so it's like the coproduct, like this and this next to each other. Like, so it knows this is different from this. It doesn't just jumble them together. That's right. This is a distinct sync one, but P sub U, I think, is P applied down, pulling down from these two. That's right, to down to this. And what this is saying is if you go up with S here, or the S from U, and then you come down with P, you will end up in the same place in U. That you would. You don't go anywhere. Yeah. Yeah. Okay, so here you still have you have the same property, right? That you have the set of all cross sections, and that if you narrow down, if you have V inside of U, you can narrow down the data over U to get the data over V, right? If you have data over a broader set, 1 and 2, you can narrow it down to have the data over a smaller set. That's true all through, regardless whether these are topological spaces or sets or categories. You're going to have this restriction map, and I want you to note that it's contravariant, right? We would denote this if we were denoting the category of sets and inclusions, what V would have an arrow to U, meaning V is a subset of U. But you'll notice that this restriction map is in the opposite direction. It takes the data on U, the bigger thing, and maps it down to the data on the smaller thing. Are we comfortable with that? Okay. Okay. Yeah, so John and I talked about this some time ago when this is applied to categories. Here, like if this is a category, now you have these as like objects in a category. These things up here are associated with different categories that could be associated with that's right. He's what we're calling P is F here. And this is a functor. So I'm sorry. So these are this is, I'm sorry. S is a category. The X is a category. These are objects within the category. These are like elements. These are like points within each of those objects. So each of these fibers is an object here. And you have functor mapping down from this to this. And you have a functor in the reverse direction of star going up here. In that reverse direction. Such that this that you still get all these properties that we're talking about. And this is where you get matters of like non-discrete op vibrations come in, because like there's amazing structure with this that comes out. It's beautiful. But the basic idea is that we have data living in a category up here. These are objects, and he drew suggestively like, well, each object might itself have some structure to it. It might be a poset, or might be some sort of set with structure, or might be a monoid or something like that. And you can have, so this might be a category of monoids or what have you. And you have some maps down for this, and then you have this reverse map up in a fashion that abides by the section properties. You map up and down. It's just identity. Okay. So this is a really interesting thing. We've talked about how, whether it's for topological spaces here, with X, Y, and P, where P is a continuous map from topological space Y to topological space X. Whether it's for this or sets, we have this feature that there's a set of cross sections over it, right? We could specify for a given open set within topological space X, we have a set, right? Do you see that? Do you see that set? For every object U might be an open set, and we have these inclusion morphisms between them. Say one open set is a subset of another, like V is under maybe V arrow U. We have a set. Do you see that? A set of sections over it. Set of sections over that set U. Is this a set? Yeah, it's a set of sections over U. Remember, we talked about that. Set of sections over 1, 2, for example. It's a set of sections, possible sections that could be, right? And we saw the same thing with set bundles too, right? There was a set of sections over each U, over each object of this category where we have sets and inclusions. There's this U is an object in this category. V would have a morphism to that object, reflecting the fact it's an inclusion. V is included in U, and for each object, we have a set over that object, that open set, equal to the set of sections over that open set. Okay, well, that should start to remind you of a pre-sheaf, where for each object, we have some set. And you'll notice that the contravariance I showed before, if V arrow U, we have a mapping tau of U to tau of V. We have a restriction map from V to U. So even though the morphism is from V to U in terms of V is included in U as a set, that means the data over V, the set of sections over V, over U, can be restricted to the set of sections over V, right? If we know the section over U, that's 1, 2, is, well, 1 is C, 2 is B, we can restrict it down to the section over 1. Well, 1 is C, right? For any section, we can restrict it down to V. Any restricted section over U, like here, C and B, we can restrict it down to a section over V, say over 1. We can do that for any of them, right? Any of this set of sections, we can restrict. Given a section, we turn it into a section over U, we turn it into a section over V, right? And that's why it's contravariant. If we have a map from V to U, we have, it's a pre-sheaf here with the op, right? So this is not merely a C set. This is a kind of like co-C set. It's not a co-pre-sheaf like a C set. It's a pre-sheaf. So there's an op here. So each object X, each open set, each U is mapped to a set of sections over it. These assignments for each thing in the base of a value here, and each morphism, V arrow U, meaning V is within U, V is a subset of U, gets turned into a restriction map from the sections over U to the sections over V, right? That restricts down the sections over U to the sections over V. And all it is each section. Well, we take that section over V over V. Does that make sense? That what we're actually specifying here is actually a pre-sheaf. It is a pre-sheaf. Okay. Because it assigns to each object in this category of sets and inclusions. It's actually the category of opens for the category. It's not just the inclusions are in there, but it's the category of opens. So we have some that are like the intersections, the unions. Those are all in there, right? And here we can narrow down the sections for U to the sections for V. And for each bundle X over X, you actually have a pre-sheaf that maps from opens of X up. So this X is a topological space, opens from X up, from the opens of it up down to set. In other words, because of this contravariance. If you have V inside U, then you have this mapping from U to V. This corresponds to map in the associated slice category as well. But I do want to highlight this actually is itself a sheaf. This is not just a pre-sheaf. It's a sheaf. And it reflects some of those properties we were talking about before. With these gluing properties, we have unique gluing for every matching family here, and we can restrict down for any subset of U and V if we have U intersect V as a self and open. That's going to have a map into U. So if we have K, we consider K the set of K in the base. That is a map into the set JK. It also is a set into a map KL. K, to be clear, is JK, the set of JK, and the intersect with the set of KL. Okay, so we have these maps. And we require for the sheaf property that this restricted to K is the same as that restricted to K. And that's what we have here. So it turns out that this set of sections, pre-sheaf, restricts down nicely. It obeys these properties. It has a single unique gluing. Restriction from U to U intersect V to the data over, so the set of sections over U, the set of sections over U intersect V is the same as narrowing down the set of sections over V, mapping down to the set of sections over U intersect V. So this turns out, as we'll see, to be a sheaf. This involves that sort of narrowing down. I call it U1, U2 here. And if you have a mapping, it glues them. You can glue them together in a single section for the union. And there's a single global section that honors this. So what we've seen is bundles here, and we've seen that for bundles, we have this set of properties involving the set of sections over that bundle, the set of possible choices over the bundle for these different values. And if we consider different subsets down here, even just for set sheaves or set bundles, we get a sheaf structure. We have this structure associated with a sheaf. We do for a topology as well. We can narrow it down, and we get all these nice properties associated with it that says that the set of sections has this nice assignment of values. If it's a topological space, it assigns it in a way that is that obeys the sheaf properties. And here P is some continuous map that we specify together with Y and X. Okay, so those are all the comments I have on bundles here. I will say bundles, for reasons I indicated here, they're an incredibly neat, interesting topic on their own, and extremely powerful. Perhaps some of you will recognize, since we've talked about the category of elements before, this should remind you of the category of elements. Each X here is associated with a set over it. The difference is with the category of elements, these are just sets. There's no morphisms here. Each of these, like this would be, maybe this is a set of vertices, this is a set of, edges and vertices. We have morphisms here from edges to vertex, like the source. And maybe this is the set of edges. This is the set of vertices. And these are functions from this set to that set for their source. And each of these in the category of elements is mapped over to one particular one here in the vertexes. Anyway, that's bundles are involved in that, as in many other areas.